practice is probably this AGP threshold theorem. And also talk a little about the overhead of photonics, which is important to know about. Okay, so this is back a couple lectures ago where I tried to give this intuition that if you have a code that can correct one error, so that if you have a code that's distance 3 can correct one error, then intuitively you should be able to get arbitrary levels of reliability, just provided that the initial physical noise rate is low enough, because you just use encoding into the code once reduces the error rate quadratically, provided the physical error rate is below. So C times P squared, provided the physical error rate is below this break-even point, which is like 1 over C, then you get an improvement. Once you get an improvement, then intuitively you should be able to repeat the procedure, concatenating to get the error rate much smaller very quickly. And even though each level of concatenation blows up the overhead exponentially. If you start with a 7 qubit code, you get a 7 squared, a 7 cubed, a 7 to the 4th qubit code. The error rate's dropping doubly exponentially. It's doubling. You get an extra square every time you concatenate. And so that means that overall it's still going to be quite efficient. So this intuition is fine. Of course, I mean it's kind of wrong. Or it can be rather wrong, because in particular it's not clear what the right definition for effective logical error rate for logical error rate is. So it's not even clear what I'm plotting here at the first level. Yeah.
So when you concatenate the schema of the error correction, when you introduce more circuits, you will introduce more errors.
Yeah.
So it's not the ideal.
It's not.
So when you introduce like signal gate, so you concatenate the quantum circuits, you will introduce the errors as you add the circuits to.
Yeah, well, I think maybe the bigger issue is that when you have physical qubits, you can imagine like a very simple noise model, like maybe they're subject to independent noise, independent stochastic Pauli errors. So for example, in any given time period, every qubit is depolarized independently with probably P or something like that. But that's fine. But the problem is once you get to the next level, once you start talking about instead of physical qubits, but blocks of qubits, then here we're trying to describe the error model on a block of 7 qubits by just a single parameter. And first of all, like that might not even be possible, because now a code block consists of 7 physical qubits, so it's obviously going to be a much more complicated channel. And then secondly, just the basic assumptions might break down, because even if the physical noise model is independent across different qubits, that doesn't mean that the effective logical noise model on these blocks of qubits is going to be independent between blocks. So that could break down, or there could be correlations in time, which there weren't in the original model. Everything could break down at the logical level. And that's just logical level 1. I mean, when you talk about multiple levels of concatenation, the noise model just gets extremely complicated. Or it could get extremely complicated, and so that's why it's hard to prove this kind of theorem. And then so actually, like a lot of the time, what people do is they don't worry about this. So I mean, they don't worry about this for several reasons. One is, in practice, you probably don't want to do more than 2 levels of concatenation anyway, just because the overhead gets rather substantial. At least, probably maybe forever, at least in the near future. But also, let's see. Also, it becomes hard to simulate, right? Because if you can simulate 1 or 2 levels of concatenation, maybe not though, right? Because 2 levels with the 7 qubit code, you're already talking about simulating 49 qubits. Which is fine if you're doing polynoise, maybe that's fine, but it's actually not even that easy to. I mean, it's not that efficient to do simulations on 49 qubits, because you got to run just lots and lots of trials to get good information. So it's just tedious. So that's one reason. And also, what people often do in practice is they look at the first, what they do is they have a plot like this, roughly like this. So here's the physical error rate, T. Here's some hopefully standard definition or reasonably well motivated definition for the logical error rate. And they just, so they do it by simulation, so they get some plot hopefully that looks like, what should it look like?